Okay, so after the huge box office collection of the last video on complex numbers, we are here with another problem where complex number makes the life of undergraduates really simpler, right? So this problem without complex number might get a bit tedious and long because there are three kind of functions involved, like there's polynomial, exponential, as well as trigonometric, right? But using complex number, we can change this trigonometric function just to an exponential, and that makes our life simpler. So let's see how it actually works. So we know that e to the power I theta is just cos theta plus I sine theta, right? So from here I can say that the real part of e to the power I theta is just cos theta, and imaginary part of e to the power I theta is just sine theta, right? Okay, so what I'm going to do is I'll just write over here. I'll just write that this integral over here, I can write it as sin x. I can write it as imaginary part of e to the power ix and then dx. Right now, since these are just real numbers, they can go inside the imaginary part. Right. So this will be imaginary part of x to the power m e to the power minus x e to the power ix dx. Now the reason I could do this is if I was trying to find the imaginary part of this thing, like these will just act like a constant because they are multiplying the imaginary part of that is sin x over here, right? So they'll just act like constant and go out of imaginary part, and yeah, this will work. Now again, imaginary part is also like linear, so that can be taken out of the integral because integral is just a sum, right? Yeah, so I can do it like this. Now the benefit of making it like this is that now there are just two functions, exponential and polynomial. So we have reduced the complexity, and now it's pretty simple actually. So this is integral from 0 to infinity x to the power m. If you take x to the e to the power x common, this will just be I minus 1, right? Dx. Okay. Now how do you integrate this? So if you are wondering how to integrate this, okay. Now you might know that integral from 0 to infinity of e to the power minus x, x to the power n minus 1 dx. This is a standard integral, right? And we learned it in the gamma function. This is just gamma of n. And yeah, if there's 1, this is a gamma of n. But if there was, let's say, some number, e to the power minus st times t to the power n minus 1 dt. In this case, you can make x, you can substitute x as st, right? And then again get this integral. So if you do that, you will get the answer as gamma of n by s to the power n. Yeah. So yeah, so you can just try this on your own. This is a standard gamma integral, and you can make a substitution to get this answer. Now over here, we need to have this form, right? So over here, there needs a minus sign. So I will make it as imaginary part of integral from 0 to infinity e to the power minus x 1 minus I x to the power m dx. Now this is the same as this one, just that here's t, here's x, that the variables are just dummy variables, that won't matter. So this will just be, now here's n minus 1, so n, here's m, so we will have m plus 1 divided by 1 minus I to the power m plus 1, right? Now after this, just try to find the imaginary part. This gamma of m plus 1 is just a real number, so that just gets out of the imaginary part, right? The reason is, now the reason is, like if you're just wondering why that happens, so let's say if I have 2 times 3 plus I. Now in this case, like the imaginary part will of course be 2 times I, right? So that's why I'm just trying to take see it as a constant. Now it's just 2I, right? So real number just acts as uh, like constant. You can see that if you must multiply, that's so obvious, right? If now you can see that it's 2I, right? So I guess you get the idea. Okay, now let's go it over here. Now we want to find imaginary part of this expression, right? So first of all, what we will try to do is we will try to express this in this form of like e to the power I theta. We will try to express that in that form. So I will just try to make them as cos theta and sin theta, right? So I divided both by 2, and also I need to multiply by 2, right? So I just divided by root 2 over here and also multiply by root 2, and the multiplied root 2 you can take that out, right? And now after this will again become gamma of m plus 1 by 2 to the power m plus 1 by 2, right? Yeah. And after that this will just be imaginary part of now 1 by this is just cos pi by 4 minus I sine pi by 4 to the power m plus 1, right? Now after this is gamma m plus 1 by 2 to the power m plus 1 by 2, and then this is imaginary part of this is just e to the power minus I pi by 4 times m plus 1. Now you can take it to numerator. So gamma m plus 1 by 2 to the power m plus 1 by 2, imaginary part of e to the power I m plus 1 pi by 4. Now this whole thing is just theta. So imaginary part of e to the power theta is just sin theta, right? So this will just be gamma of m plus 1 by 2 to the power m plus 1 by 2 sine of m plus 1 pi by 4, right? Now we know that gamma of m plus 1 is just m factorial, so this is m factorial by 2 to the power m plus 1 by 2 sine of m plus 1 pi by 4, and that should be the answer. Now let me just check the answer because I do have an answer key for this one. And the answer, let me see if it's matched or not. So m factorial, okay. The answer is m factorial by square root of 2 to the power m plus 1, which is same, and then sine of m plus 1 pi by 4, which is also same. So yeah, the answer matches, and this is the answer. So to summarize the solution, we just express sine in terms of the imaginary numbers, and then we use the gamma function, and then we try to extract out the imaginary part, and that gives us the answer. So this was it, guys. Hope you enjoyed the video. Thanks for watching, and look forward to seeing you in the upcoming videos too. Just try to engage with the content. I hope that they're really helpful, especially in getting the intuition or getting feeling of why something works, right? So that's the major purpose of this channel, and hope it's been helpful.